Okay, my name is Qianming, and today I'm going to share some information about the spiky neural networks, a kind of brain-spared computing. So firstly, let's have a look on the evolution of neural networks. So in about 80 years ago, the first generation neural networks are invented. In 1943, the MP neural was introduced. It simulated the neurons structurally, but it only did logical calculation, and all parameters are assigned by humans instead of by learning. In 1957, perception was invented. It composed a lot of MP neurons, and it induced the Heaviside step function, which is a kind of activation function. Besides, the parameters of the network were not assigned by human directly. They update according to this formula. However, there are some problems for the first generation networks. It cannot solve nonlinear problems. You cannot find a line which splits the red squares and blue dots appropriately, and the Heaviside step function is not differentiable. That is why perception cannot update its parameters according to a dynamic formula. Then scientists did some improvements, which led to the emergence of the second generation networks. They use the differentiable activation functions. That means the neural networks can use the gradient to perform the backpropagation and update its parameters dynamically. They also introduced the hidden layers that allow networks to grow much deeper, giving them better capacity. Now, with these two improvements, the networks can approximate nonlinear functions. Those second-generation networks are called artificial neural networks or deep neural networks, which are what we are learning right now, such as MLP or the SNNS. So the second generation of neural networks simulates the structure of the biological neurons, but it doesn't simulate the actual mechanism of information transmission between neurons. And there's no inherent temporal encoding. That means if we want to solve some issues regarding the time series, we need to build a new architecture artificially, such as RNNs. Besides, it is very energy consuming because we need to use GPUs to compute the gradients in parallel way. Thus, scientists introduced the discrete specs rather than the continuous numbers to represent the information transmitted between two neurons. This kind of information representation is event-driven. That means it's very energy efficient because each spec can be seen as an event. The most important point that the third generation of neural networks doesn't need backpropagation. With those improvements, we have the third generation of networks that is spiky neural networks. So SNNs are based on three core biological principles. The first is membrane potential integration. That means the current neuron integrates the specs transmitted from previous neurons. When the accumulated value exceeds the threshold, it fires a spec. After that, it enters a refractory period, and during which it doesn't react to any incoming specs. These three principles form the foundation of the basic neural model used in SNNs, which is the leaky integrated and fire neuron, the leaf neuron. So the specs is the core essence of SNNs. If we want to use the SNNs, we need to find a way to encode the data into specs. Let's think about how do we perceive the world at first. We use our eyes to scan the environment. So the light is what we see when retina covers photons into specs. And then those specs are transmitted on axon between each neurons. Finally, the specs reach a specific area in our brain which is responsible for the vision. We can find that specs are actually a series discrete single-bit events. We can represent it using the binary numbers, which are really common in the computer. So in the biological system, the specs are naturally sparse. On one hand, the spacetite saves a large amount of energy. On the other hand, it reflects the fact that our sensory system mainly responds to changes. For example, a moving car. Objects that do not change, like a static background wall, typically do not trigger the strong response. This property, firing specs only for changing or moving stimuli, is known as a static expression. So from the hand-waving example, you can see that the specs appear only in the fingers, which are the parts actually moving. And the stronger or the faster the change is, the denser the specs become. Okay, now we already know how to represent the specs in computer, using the binary numbers and the characteristic of specs, which is space-state and static expression. What should we do? Let's say if the input is already in specs, that is great. We don't have to do anything to convert the data into the specs anymore. However, most of the input data is not in such format, such as the pixels is a real value, it's a real number. So how can we transfer a raw data into specs? Also, how can we transfer a real number in a series of specs? Actually, we have 3 methods that can solve this problem. The first is Rethinking. We can convert the input features to the spiking frequency. And the second one is lattice encoding. And the third one is delta modulation. Now let's have a close look at the 3 methods. So for the first one, the rate encoding, we normalize the input data to the 0-1 range at first. And then we get a lot of normalized input features, XIG, that is the pixel value and row I and column G. The value of XIG corresponds to the probability of specs at each time step. So when the input is 0, at each time step, the probability of firing a spec is 0. So you can now see any specs in all time steps. If input is 0.5, the neuron fires spec every other time step. If the input is 1, there is a spec at each time step, but all of these only happen in the ideal case. So finally, we get the new data in 3 dimensions. The new dimension is the number of steps. With more steps, we can better approach the probability. The second one is lattice encoding. In that case, normalization is not necessary. We just need to make sure the range of the input value is in the domain of the function. So this follows the principle that the larger the input value, the earlier the spec is fired, just like that. But this is only a qualitative description. To quantitatively determine the spike timing, we typically rely on a specific function. The output shown here shows the blue curve, follows the blue curve. You can see that the spike times cluster into 2 regions. This behavior is somewhat extreme because it causes the model to fire too many specs within a short time window, potentially exceeding the model's processing capacity. Therefore, in many cases, to ensure more evenly distributed specs timing, we prefer the yellow curve instead. So the last one is quite different, but it is most biological inspired, like what we have learned on the last slide. Our sensory system mainly responds to the changes. Imagine we have a sequence of numbers, say an audio wave. Delta modulation takes the difference between each number and firing the specs following this algorithm. So if the absolute value of difference is bigger than the threshold, then X is whether the difference is positive or negative. If it is the positive, firing on spec, which is represented as 1. If it is negative, firing an off spec, which is represented as -1. Thus, we need to use 3 different numbers representing specs, and this method works for sequential data only. So it's time to introduce the cornerstone of SNNS, which is leaky integrated and fire neuron, the leaf neuron. Let's start by looking at a circuit. This circuit simulates the working mechanism of leaf neuron at the physical hardware level. It is a classic RC circuit composed of a resistor and a capacitor. So this figure shows the timing of input current, and this component is responsible for monitoring the voltage across the capacitor, the V. So when the voltage exceeds the threshold, it generates a current spec. Then we can use a mathematical language describing this circuit. So the current flowing into a capacitor equals the input current minus the current flowing through a resistor. So I sub C equals to the derivative of Q with respect to T, and I sub R equals to the V over R. So then we can combine these three equations and finally get this equation. And after that, we can reorganize this equation into this format. So the tau sub m equals to the R times C. It is a constant term. And then we can divide both sides by the tau sub m. Finally, we get this equation. This formula describes how the voltage of capacitor C changed. The first term is leakage term, which measures the loss caused by the resistor arm, and the second term is integrate term, which measures the total input. So this formula describes how the voltage across the capacitor changes in response to the input current. Next, we can relate this circuit to a real biological neural model. The capacitor C can be viewed as the cell brain. So because the membrane can store the charge across its two sides, just like a parallel plate capacitor. So ion channels act like the resistor. And since they allow the current to leak out, and the resistance value determines the leakage rate. When the membrane voltage reaches the threshold, the neuron fires a spec. To implement this on a computer, we need to discretize this equation. We can reorganize this equation, and finally, we get that. So this equation is very similar to that of ANNS. The final output is determined jointly by the previous voltage and the current input. By manually tuning these parameters and these parameters, we can control how much the model should emphasize the current input versus the information carried over the previous steps. Now that we understand how the membrane voltage evolves, and the next step is to determine under what conditions a spec is generated. Clearly, this firing function resembles the activation function used in ANNS. The difference is that it is actually a non-differentiable piecewise function in which the threshold voltage is a hyperparameter that can be manually set. After a neuron fires a specs, it needs to have a rest for a moment. So during this period, the model enters a refractory state, and the membrane voltage drops back down to the resting potential. Now we have fully explained how a spec propagates and is generated along one pathway. The dynamic on other pathway follows the same principle. So in the end, we obtain the following equations. Beta controls how much the model attends to the previous membrane voltage and can be viewed as a form of memory. So the W represents the parameters the model needs to learn. It is the value that assigned to each length. The final term is responsible for reciting the neurons. So after firing spec, it returns to a resting potential. With this, we complete the forward pass of the model. Now let's look at how the model updates its parameters, that is, how it learns. The most straightforward approach is gradient descent. Although I mentioned earlier that SNNs no longer depend on the gradient descent, this doesn't mean that SNNs cannot use it. After all, the prior knowledge accumulated by scientists on gradients and backward propagation is extremely valuable. From this computation graph, we can see that the forward pass of the model can be unrolled through the time, and it indeed looks very similar to an RNN. So after time step T0, T1, T2, and so on, the model doesn't feed the output directly, right, into the next step. Instead, it passes the membrane voltage to the next state. Therefore, by referring the backpropagation through time, the BPTT, it has used in ANNS, and we can derive the formula for the partial derivative of loss function L with respect to the parameters W. So this corresponds to following the red dash and applying the chain rule at each segment, and finally summing over the time dimension. However, we mentioned earlier that the firing function, let's say the activation function in the SNNS, is a piecewise function. As shown in this figure, it is now differentiable. So during the gradient computation, we found that the derivative of Sn with respect to the ut doesn't exist. It is either 0 or infinity. This makes the gradient calculation impossible to the gradient descent and directly leads to what is known as the dineuron problem. So how can we solve that? One solution is that in the forward propagation, we can use the original firing function to transmit the information between two neurons. But in the backward propagation, we use the gradient of similar activation function to approximate the derivative of ST with respect to the UT. For example, we can use the sigmoid function, which is pretty similar with the figure show of firing function of SNNS. Then we can use the derivative of sigmoid with respect to UT, simulating the derivative of ST with respect to the UT, since sigmoid function is differentiable. So another way to update the parameter is much more biologically inspired. It is designed entirely for SNNs and completely abandons the gradients, which often feel very difficult to calculate and give a heavy calculation burden to the GPUs. So this method is called the spectrum timing dependent plasticity, or STDP. So STDP is an unsupervised learning algorithm, and this is also one of its limitations. The STDP algorithm is based on the discoveries of Gongqiang and Muming. They found that if pre fires a spec first and then post fires a spec, the connection between the pre and post neurons will strengthen. But if the post neuron fires a spec first and then the pre neuron fires spec second, the connection will be weakened. So the figure shows that the result obtained. This figure shows the result obtained from the biological experiments. The horizontal axis represents the time difference between the pre and post spikes. The vertical axis indicates how strong the synaptic response is compared to the baseline. So from the plot, we can see that the shorter the firing interval, the stronger the effect is. And on the left side of 0, the synapse is weakened. On the right side of 0, the synapse is strengthened. So based on this, we can define this rule. The parameters update between the pre-neuron I and the post-neuron G depends on the spec time Ti and Tg. So if Ti is smaller than Tg, it means the presynaptic neuron fire earlier, so the synapse should be strengthened. Conversely, if Ti is greater than the Tg, the synapse should be weakened. However, this approach has a major drawback. So to perform pairwise comparisons, we must record all specs and all links. So if we have n pre-neurons and m post-neurons and the number of time steps is t, then the space complexity becomes O(n) times m times t plus m times t. And since every spike pair must be compared, the time complexity becomes n times m times t squares. Earlier, when we discussed coding schemes, we mentioned that for large T, rate encoding becomes more accurate. But this also means the computation cost grows significantly. This imposes extremely high storage and computation pressure on computers. Therefore, we can optimize the algorithms leading to the tree-based STDP. The key idea of this improved method is we no longer compare row stack times. Instead, we compare tree-based potentials. Intuitively, a tree's value represents the recent hit of firing history. The more recent the stack, the hotter it is. The longer it has been, the cooler it becomes. So the second term handles the cooling. The third term corresponds to the firing function. With this optimization, we no longer need to store all stack times. We only need to maintain the current and the previous stacks. In terms of computation, we now only need to iterate through the pre and post neurons once, so the time complexity drops to O(n times m). And another good thing is that we don't have to wait for recording and comparing. In the original one, we don't need to backpropagation anymore. We need to wait for the recording and computing after each forward pass in each segment. Now, we can update at each time step. That means we can update the parameters while performing inference. This is clearly more efficient and also more human-like. We don't suddenly stop speaking mid-distance and run back propagation inside our brain and then resume the talking. That would obviously be ridiculous. And by the way, the hyperparameters in this rule is A, B, and tau. Yeah, and this two part is also the hyperparameters, but I prefer to call these two as maybe a hyperfunction because the input of each function is the parameters of the each links. So besides these two methods we have mentioned before, one is surrogate gradient descent and another one is STDP. There are also two methods that we can use for the training. So the first one is AN to SN conversion method. It is widely used in industry. It is obviously that this approach makes full use of all the knowledge we have accumulated about ANs. And we first train an AN as the base network. Then we record the maximum activation value for each layer, which will be used later in the conversion process. After that, we replace the AN's ReLU function with the quarterly firing function used in SNNS. In other words, we convert AN neurons into leaf neurons. The key principle here is that the larger the ReLU output, the more stacks the corresponding leaf neuron will emit. So we take the train AN parameters and rescale them using the recorded maximum activation value. This ensures that the sum inputs to each leaf neuron are neither too large nor too small. Otherwise, the neuron would never stack or stack continuously, which is pretty similar to gradient vanishing or exploding in ANs. So finally, we set an appropriate firing threshold. The advantage of this method is clear. It fully leverages an AN as a training tool. However, the drawback is that the entire training process is unrelated to SNNs. The SNN is effectively just an AN wrapped in a stacking shell. In essence, this approach represents a compromise due to the current and development of native SNN training methods. Another method is introduced by Hinton, called forward-forward. So this method also doesn't require the backpropagation. Instead, it relies on two forward passes. In the first forward passes, the positive examples is fed into the network. So at each layer, the network computes a goodness value and applies a log-based local loss function. So the goal of parameter updates at each layer is to maximize the goodness, which is equivalent to minimize the local loss, that is making the goodness as large as possible relative to threshold. After processing the positive examples, the second forward pass feeds the network negative examples. For those negative examples, the goal is to minimize the goodness, meaning that we want the goodness to be as far below as threshold as possible. Again, this is achieved by minimizing the local loss function. So the structure of this loss is similar to what we encounter in maybe in logistic regression. I think that is. So fundamentally, this method is not specifically designed for SNNs. It works for both ANNs and SNNs. It represents a general perspective on parameter updating that, compared with backpropagation, aligns more closely with biological intuition, much like the philosophy behind SNNs. So now we have calculated both the forward pass and the backward pass of the model. The weighted specs have reached the final layer of the network. So the last step is to decode the spec into the outputs that humans can understand, such as the real numbers or labels. You can think of decoding as the inverse process of encoding. So we can decode using the number of specs, which corresponds to the inverse of rating encoding. We can use the time of first spec, which is inverse of latency encoding. Another option is interval between the specs, or the distance between specs, which can be viewed as a variant of time-based decoding. However, the most commonly used method is decoding based on the membrane potential. So we simply take the membrane potential of the neurons in the final layer and the final time step as the model's output instead of feeding that value into the Fang function. So this provides a smooth, continuous output that is easy to interpret. The loss function used here are no different from those in ANNs. So those loss functions are mainly used for surrogate gradient descent because it is the supervised learning. And in an STDP-based unsupervised learning method, such loss functions serve more as metrics rather than true training objectives. So we already know how to implement the SNNs in the software. Now let's talk about how to implement it in the hardware. And I want to emphasize a key point that when we train spike neural networks, the SNNs using traditional CPUs or GPUs, the computation cost is actually higher than training non-spike neural networks such as ANNs. So although SNNs are theoretically energy efficient, this advantage doesn't automatically appear on general-purpose hardware. Because the outputs of an SNN are binary specs, the network must unfold over multiple time steps to represent a continuous value. In other words, if an ANN can process a real number in a single step, an SNN may require t time steps to generate the corresponding spec sequence. So this temporal unfolding directly results in a significant increase in computational workload. This figure on the left illustrates an FPGA-based SNN pipeline. FPGA is kind of chip which can be programmed. As shown, the hardware workflow includes modules such as input buffering, convolution, membrane potential updates, and the spec generation checks. So these implementations still relies on digital logic to simulate neurons requiring clocked operations and explicit numerical computations. Therefore, although it is specialized for the SNNs, it doesn't truly achieve the high energy efficiency of neuromorphic computing. This right side shows the Tianjic chip. Unlike FPGAs or GPUs, this chip implements neurons and the synapse as dedicated circuits and uses an event-driven execution model. So if no specs occur, no computation is triggered and no energy is consumed. Inside Tianjic, the F-core array can run a large number of neurons simultaneously and independently, so closely resembling the parallel processing style of biological neural networks. This architecture allows SNNs to truly realize their energy efficiency advantages. So that's everything I have for the SNNs, and thank you for watching. If you are interested or have any questions, feel free to reach out. Thank you.